Hello and welcome to the course of Introduction to Astrophysical Fluids. So, in the previous lectures we discussed basically the basic concepts of the dynamical theory and how we can promote from one dynamical theory to the other, starting from the very basic quantum mechanics to the classical physics of a small number of particles, and then we also said that if the number of the particles are high enough, then we will use the statistical description, thereby leading to the kinetic theory. And also if finally there is another level which is basically our principal objective to derive the dynamical theory for that level, this is the level of fluids or continuum, right, that we will do of course in the next part of this course. Okay. Gradually we will develop the equations of a fluid. Now, I ended the last lecture by deriving a very basic theorem of statistical mechanics which is known as Liouville's theorem or Liouville's equation, and I also derived a corollary from that. So, let us recapitulate some of the points of the last lecture in a global way. If you remember that you have a system of n classical particles which are identical to each other, but can differ only in mechanical states, then if you remember that the complete state of the system will simply be denoted by a single point of gamma space. Now, as I said that if you are just considering 3-dimensional real space and the motion of the particles in this, then for every particle you will have 6 coordinates or 3 coordinates from position and 3 coordinates for velocity, and then for n. So, for one particle you will have r and v. Okay. This is also equivalent if you are as I just used in Liouville's theorem in the last lecture, that the Hamiltonian mechanics and a Hamiltonian formulation, then I had to use r and p. Okay. But p is the momentum. Okay. So, for non-relativistic case they are actually very, they are similar. So, you can simply write r and v for one particle in phase space. This is their designating coordinates. So, 3 coordinates for r because 3D space and corresponding 3 velocity coordinates for the particle. So, one particle gives 6 coordinates in phase space. Okay. Then for capital N particles you will have 6n coordinates. So, if you assume your phase space to be of phase space of 6n dimensions, that is basically your gamma space as I said, then if you just freeze your time and take a snapshot, then basically only one single point will be will designate the complete state, or rather complete dynamical state or mechanical state of the system at a given instant, let us say t. Then of course, by varying t you can also have other pictures. So, there can be two type of alternative description. One is that you say my phase space will be of 6n dimension and then I vary the time as a parameter, or you just say that my complete phase space will be 6n plus 1 dimension. Okay, that is possible, but here we are just talking about 6n dimension phase space and just we are using time as a parameter. Okay. Then if you now assume all the particles are there which are classical particles, and at some time t you take a snapshot, then this particle will have some RV, let us say RIVI, this particle will have let us say R1 V1, this can be R2 V2 for example, okay, this type of thing. Then we said that if you now take one combination of all 6n type of coordinates, let us say, so if I just write R is equal to x, y, z, okay, the triplet, and V for x dot, y dot, z dot, then ensemble of numbers x1, y1, z1, comma x2, y2, z2, xn, yn, zn, okay. This 3n numbers plus if you write x1 dot, y1 dot, z1 dot, xn dot, yn dot, zn dot. Okay. So, now I just combine all of them, sorry, you can have 6n number of coordinates, and that is one single point in your gamma space. Okay. So, that is your gamma space, it will give you simply one single point. Okay. This is gamma space. I said again that we can also define another phase space which is mu space. Then for every single particle, the complete mechanical state at one time, for example, is designated by one single point. Okay. And we can only switch from gamma space to mu space if we have particles which are identical to each other and they can just differ from each other by mechanical conditions, right. Only that means in terms of their position and velocity. Now, you can see that one single point is mapped to n points, right, every point having 6 coordinates. Okay. And then I said that when this particle is led to evolve, okay, in time, maybe it evolves along this trajectory, then in mu space they will have a large number of, I mean rather you can easily calculate n number of trajectories. Okay. So, that was the whole picture, and then I said that let us define a concept which is the concept of ensemble. So, the concept of ensemble is that you can basically you can assume that at a given instant t, so ensemble is nothing but at a given instant t, ensemble is the collection of all the possible states of the system. So, this is something which is ideally an imaginary creation. What practically we do, that if the system is ergodic, we say if the system is ergodic, okay, then the system is observed for long time. Then we can see that, and at every moment or at every instant, for example, if your instance of, I mean if your speed of, if you take one snapshot every second, for example, then what happens, that at every second you just capture the information of the state. Okay. So, for every second you have one single point of gamma space, right. Then after a sufficiently long time, you have a collection of such states, right, okay, or collection of such gamma space points. Okay. Then you say, if the system is ergodic, then instead of observing the system, okay, throughout this long time interval, now let me do an equivalent approach. That means, I say that the system, if when observed throughout a long time interval gives all these states, possible states, then if I freeze my time, then I can actually imagine that it is also possible that I can make at one given instant all these possible conditions or the possible states as the replica of the system. Okay. That means, by some trick you have made or you have prepared, let us say you have taken 1000 pictures, okay, in 1000 seconds. Now, you say I take all the information of the 1000 pictures, every picture contains information of the 6n coordinates, 6n I mean there will be 1000 combinations of 6n variables. Okay. Then you say that I will now imagine that this is equivalent, that I am taking the system or I am observing the system at one single time instance, okay, and then I imagine that my system is prepared in 1000 multiple replicas, and these collection of replicas are known as ensembles. Okay. So, one real point in gamma space is nothing but a member of the ensemble, or we say a point of ensemble. We also defined that if the members of the ensemble, point of the ensembles are sufficiently densely situated in the phase space, then what happens, that we can define a effective density for the states, okay, and we say that this is the density of the ensemble, and we call that, if you remember, we call that rho ensemble. Okay. Then finally, we talked about Liouville's theorem, and which simply said that if we follow the evolution of this rho ensemble along any of the trajectory of the members of the ensemble, then we will have d rho ENS dt will be equal to 0. So, let me just draw here, so that there is no confusion. I have an ensemble and all the ensemble points are there. So, basically one single point in gamma space already corresponds to n points in mu space, but forget that. I am now talking about a large number of points in gamma space. So, these points are nothing but the replicas of the system, okay. And every point, if is left to evolve, they will evolve separately according to some law. Okay, I do not know which law, but that depends on the system. Okay. And then you see that basically if you follow any of those trajectories, any one, okay, any one, but you have to follow one trajectory and then you just continue calculating, for example, rho ENS along the trajectory, with time it will be constant. So, that was the statement of Liouville's theorem. Then we also said that there is a corollary of Liouville's theorem which simply said that the elementary volume containing a given mass of density points, or I mean a given mass of ensemble points, okay, will be behaving like an incompressible medium. That means product of dqs dps will be summation over s dqs dps with primes. Okay. So, that I said. So, today we will try to understand. So, that was the story for gamma space. Okay. Today we will try to understand what is the story for lambda, I mean mu space. Okay. So, can we also define such type of density of states in the mu space? Well, the answer is yes, we can define. So, my question is, what happens at mu space? So, in mu space we can actually define in a similar fashion, okay, a density of space, density of ensemble points, But whenever I talk about density, now you have to remember that every single point in mu space is a single particle state, right, at a given instance. Okay. So, density of ensemble point is possible to define. Now, the question is when. Let me do like this. I take a very small volume element in mu space, very small, delta V tends to 0. Okay. Now, I write delta V tends to 0 plus, that is because okay, that delta V is a very small volume element with respect to the total volume accessible in the mu space, but delta V is sufficiently large, is large enough to contain sufficient number of states. Okay. Of course, you know when I talk about states, that is the state corresponding to one single particle. Okay. So, whenever you, I mean basically if one point, for example, in mu space corresponds to the state, for example, at a given time for first, I mean particle number 4, then another point can denote the state of particle number, let us say 15, okay, at the given time instant. So, this delta V should be large enough to contain sufficient number of states, so that we can define some density. That is exactly the same thing, the same philosophy which we used for gamma space. Okay. Then, if we have delta n number of points in delta V, we can define the corresponding density of states. We use the symbol f, and which will now be a function of r, u and t. Okay. So, r is the position, u is the velocity, t is the time. Okay. So, again you can see that now we are interested that, so this is one single point of mu space. So, it is not, it is simply, so mu space is 6n plus 1, I mean, so 6n dimensional space, okay, including t 6n plus 1 of course. So, you will have a collection of particles in some volume with the limit v tends to 0. Okay. If this limit exists, then only we can say that the system has, or the corresponding mu space has, a legitimate density of states. And this is known as the distribution function. Okay. So, only when this distribution function is well defined, then one can go from normal classical theory level to statistical description using kinetic theory. Okay. We saw that under some given condition we can define a density of states which we call formally a distribution function f, which is a function of r, u and t, of course. Okay. Distribution function which is the density of states in mu space, that we can define. Now, the question is that can we also derive Liouville's equation for mu space as we derived it for gamma space? Well, that is not evident. Okay. Now, of course, if you really followed attentively the derivation of Liouville's equation, you have to understand that the key factor in Liouville's theorem was the Hamilton's equations, and that Hamiltonian was defined because the system was without dissipation if you take the total system under consideration. Okay. That means, the system was an isolated system. Okay. If you just consider the total system as a whole, basically there can be interaction between two particles, okay, but there was no source of energy from outside, or there is no sink of energy outside. So, the system as a whole does not gain any energy, and similarly it is not losing any energy. Okay. That is why this is a conservative system and we could define a Hamiltonian. So, for the entire system, defining a Hamiltonian was evident as it was isolated. Okay. Bracket, although could include interparticle interactions. Question is, can we define a Hamiltonian for mu space? The first level answer is no, in general. Okay. So, does that mean that we do not have any hope? Okay. So, of course, here when we say Hamiltonian, that would be a Hamiltonian which is a function of r u and can be maximum a function of t. Okay. So, here the Hamiltonian means the Hamiltonian of r u and t. Okay. So, can we have some good news using some assumption or something? Well, now try to think that considering a particle at r and u, okay, interacting with another particle at r prime and u prime. Okay, those two particles are maybe interacting with each other. Okay. Then we know that they are for them, as they are just moving under their mutual interaction, we can define a Hamiltonian, which simply is nothing but mi Ri dot square. Of course, here the summation is on r and r prime, okay. And then you will have this phi r prime r. That is possible, but how to incorporate this type of thing in mu space? How to incorporate in mu space? This is not possible, because in mu space we just permit r, u and t and no r prime. Okay. This is a single particle state. Okay. So, the answer is very clear that in general, although it is not possible, h mu r u t can be defined if we neglect or we remove all sort of interactions between particles. Okay. That does not say that on each particle there is no force or nothing. There can be some external force or something. Okay. So, the particle can be moved in an external field. Okay. The particle can move in an external field. For example, if you have a container of gas molecules, okay, but they are not colliding with each other, they are not attracting or they are not repelling each other, but all of them, for example, the total container is put on earth. So, all of them are experiencing earth's force of gravity. Okay. So, this is the instance where you can think that there is no interparticle interaction, but all the particles are moving, okay, under the action of gravity, and here you can see that in the potential form only the instantaneous position of one single particle will be there to to write the Hamiltonian of the system, and external force fields usually are conservative in nature. So, we can write the Hamiltonian for every single particle like this. I just say mu space Hamiltonian. Here you can easily see that I have just used sometimes p, sometimes u, but sometimes v, but try to understand that so basically u, v, all of them are here just used to define the kinetic space velocity. Okay. So, it is the particle velocities. Okay. Now, if we define that, then we are actually done. Then you can say that I can derive or I can obtain Liouville's theorem, Liouville's equation rather, equation for f r u t as well. And that is very important message. So, you can say d d t if r u t is equal to 0 only for non-interacting systems or non-interacting particles. Okay. So, if your df dt is equal to 0, then what is the meaning of corresponding ddt? That is something very interesting. Here ddt means, so in gamma space, if you remember, that ddt was along the trajectory of evolution of one single particle or single point, one single point of gamma space. That means, the evolution from one single, from one global state having 6n coordinates to any other subsequent global states. Okay. So, that actually was the evolution of the whole system, the trajectory of evolution of the whole system. Okay. Here ddt has a separate meaning. Here ddt simply means that we are following the trajectory. So, along the trajectory of evolution of one single particle, because every single particle just says or one single particle state, that is it. Okay. This one, just you know that this is evident to write. If you have df dt is equal to 0, you can see that del f del t will be, so f is a function of r, u and t, del f del t plus del f del r vector. So, this is nothing but a style of writing gradient of f, okay, dot r and dr dt plus del f del u dot du dt, okay, that is 0, that we have obtained. Okay. So, what is this? This is del f del t is okay, but what is this? Del r del t, dr dt. What is this? So, dr dt is nothing but the particle velocity itself again, right. This is the the total time derivative of the position. So, this is nothing but u dot gradient of f. So, this is gradient of f plus this one is du dt. Now, we said that the particle can be subject to external fields, force fields. So, let us say that external force field, which is assumed to be conservative, of course, is f, then this is nothing but the acceleration. So, I can write f by m, where m is the mass of the particle, okay, one single particle, and actually for every particle, because they are identical to each other in general. So, f by m, this one I just write using this symbol, gradient in velocity space, that is equal to 0. Okay. This equation is known as collisionless Boltzmann equation. This equation also has another name, it is called Vlasov equation. Okay. Now, why collisionless? Because we could use the Liouville's theorem and hence derive this only for collisionless gas. Okay. As you will see that I will discuss nextly, that if the system is not without collision, okay, that means with collision, then the right hand side is no longer 0. Okay. Okay. Thank you.